In section 7.5.2, we'll learn how to find derivatives of inverse trig functions. Let's begin with the problem of finding dy over dx for y equals arcsine of x. At this point, we don't know the derivative of arcsine of x, but we're going to use techniques that we've learned to derive the derivative. Now, if y equals arcsine of x, then we could say sine of y is equal to x. We're simply taking the sine of both sides of that equation. In this form, we can take the derivative implicitly of both sides with respect to x. So we're going to find the derivative with respect to x of sine of y. And we'll set this equal to the derivative with respect to x of x. Now, the derivative of sine of y, notice the mismatch in the variables. The independent variable is x, and I'm working with an implicit function of x here. So we need to differentiate the outside function, derivative of sine is cosine, and then multiply by the derivative of the inside function, which with implicit differentiation we represent as dy over dx. On the right side, the derivative with respect to x of x is 1. Now, solving for dy over dx, we end up with 1 over cosine of y. But because we began with an explicit function, we should be able to obtain an explicit derivative. And we've learned that we can do that by replacing y with its original function in terms of x. So we have dy over dx equals 1 over cosine of y, which originally was arcsine of x. Now, this is definitely not the simplest form of the derivative. We can evaluate this composite function. We'll do this in the same way that we did in the previous video. Let's suppose that some angle theta is arcsine of x. Then sine of theta is x. And again, we just took the sine of both sides of that equation. Well, if theta is an angle on a right triangle and sine is opposite over hypotenuse, since sine of theta is x, we could say the opposite side is x and the hypotenuse is 1. If we apply the Pythagorean theorem, we can solve for this horizontal segment as the square root of 1 minus x squared. Now that our triangle is set up, we can go back to evaluating cosine of arcsine of x. So now we need to find cosine of theta. Well, cosine is adjacent over hypotenuse. So derivative of y with respect to x then is 1 over square root of 1 minus x squared. Thus, the derivative of arcsine of x with respect to x is the square root of 1 minus x squared. Now, make a quick observation before we move on to the other formulas. We started with a function that is transcendental. That is, it's of the variety of an inverse trig function, an exponential function, a logarithmic function, and we ended up with a derivative that is an algebraic function. This happens with logarithms as well, right? The derivative of natural log of x, for example, is the algebraic function 1 over x. Now, if we did this same process for the other inverse trig functions, we could use a similar approach. These are the formulas that we would obtain. Now, please be aware that the formulas here on your notes are in the most general form. So instead of just considering inverse sine of x or arcsine of x, we're going to suppose, what if the argument is a function of x as opposed to just an ordinary x? In that case, we would apply the derivative pattern that we just derived. Remember, we figured out 1 over the square root of 1 minus the argument squared. Well, if the argument happens to be a function of x, we're going to multiply by its derivative in the numerator. Now, this looks like 6 new formulas, but actually they come in pairs. So if you can memorize the first 3, the derivative of inverse sine, inverse tangent, and inverse secant, then notice that their complementary functions are different only by a sign. Oops, cotangent, please fix the typo. The derivative of inverse cotangent should have a negative attached with it. So again, if I look at the derivative of inverse sine, the derivative of inverse cosine follows the same pattern, but it has an opposite sign SIGN. If I look at the derivative of inverse tangent, the derivative of inverse cotangent has the same pattern, but opposite sign. And finally, the derivative of inverse secant has the same pattern, but an additional negative. So if you memorize those top 3 formulas across row 1, then remembering your cofunction relationships, you can simply attach a negative to get the other 3 formulas. Now let's see if we can apply these particular formulas. Find and simplify the derivative. So if h of x is arc sine of x, h prime of x is going to follow this first formula. So notice in the denominator we have the square root of 1 minus u squared, or 1 minus the argument squared. And in the numerator we have u prime, or the derivative of that argument, which is 1/4. So the calculus on this step is complete. We have found the derivative. The rest is simply going to be algebra, and this sometimes is the most involved part of the problem. We need to simplify this complex fraction. So I'm going to begin by squaring that element under the radical in the denominator. We have 1 minus x squared over 16. Then let's go ahead and get a common denominator in the denominator of 16. We could rewrite that as 16 minus x squared over 16. Then, using rules of radicals, we could split the radical in the top and the bottom to obtain square root of 16 minus x squared over the square root of 16. Then the square root in the denominator can simplify. So we have the square root of 16 minus x squared over 4. Now, if you want to see the algebra on this, since we have a complex fraction, we could multiply the top and the bottom by 4. Now, watch what happens. The 4 in the numerator cancels, and the 4 in the denominator cancels. See if you can observe the big pattern here. Notice that our original denominators were the same. If you have a denominator in the numerator that matches the denominator in the denominator, they're going to cancel every time. And of course, you can prove it algebraically like we did over here. But our final result, h prime of x, is 1 over the square root of 16 minus x squared. Now, as you're working your derivative problems in your homework and in your labs, observe the relationship between the original function and the resulting function. We started with a transcendental function, we ended up with an algebraic function. So eventually, we're going to reverse this and look at integration. In order to yield an inverse trig function, we're going to be dealing with integrands that are algebraic. Okay, let's try another example. We want to find the derivative of g of x, which is inverse cosine of x squared. So to find the derivative of g, we're going to begin with our power rule. We're going to take the power down in front as a coefficient. We're going to keep the base the same and decrease the exponent by 1. Then I'm going to write out my plan here. We're going to multiply by the derivative of that base. So our next step is to find the derivative of inverse cosine of x. And we've got our formula up here. Notice instead of a function of x in the argument, we have an ordinary x. So our derivative, starting with this, 2, and we can simplify this to inverse cosine of x. The derivative of inverse cosine of x, we're going to have a square root of 1 minus x squared in the numerator and a negative 1 in the numerator. Hope I said that right. So our final result, if we want to make it all one fraction, negative 2 inverse cosine of x divided by the square root of 1 minus x squared. It's a little easier going in this direction. Eventually, we'll start with an integrand that looks like this, and by a u substitution, we would integrate to obtain this. On the next problem, we're going to differentiate an inverse secant function. Now, the formula is listed above on your notes. I'm having a little hard time with my scroll feature here, so I'm just going to record it down here. The derivative with respect to x of inverse secant of u is equal to u prime divided by the absolute value of u, and notice u is just the argument, times the square root of u squared minus 1. So following this pattern, the derivative of f, we can call it f prime, we're going to start by differentiating the outside function, that is the inverse secant, understanding that the argument, natural log of x, is going to stay the same and have an effect with the chain rule. So according to the pattern, in the denominator, we're going to have the absolute value of the argument, which in this case is natural log of x. Then we're going to have the square root of the argument squared, natural log squared of x minus 1, and now we're ready for the chain rule part, the derivative of the argument in the numerator. Well, the derivative of natural log of x is 1 over x. To simplify this complex fraction, we're going to multiply the top and the bottom by x, and this will give us 1 over, I'm going to move this little monomial term to the left, x times the absolute value of the natural log of x times the square root of natural log squared of x minus 1. I don't know about you, but that is a beautiful derivative, right? Maybe a little complicated. All right, let's practice another example. Derivative of 6 arctangent of x over 3 plus an algebraic function. Again, the derivative formula is listed up above on your notes. But I'm going to go ahead and write the derivative of arctangent, which is the same thing as inverse tangent, right here for reference. U prime over 1 plus u squared. So to find dy over dx, first of all, notice we have a constant coefficient 6. That's going to filter through to the derivative. Then I'm going to follow this pattern to differentiate the arctangent of x over 3. The argument here is x over 3. That's going to be in place of u. So on the bottom, we have 1 plus u, x over 3 squared. And in the numerator, we have u prime. The derivative of x over 3 is 1/3. Now, as far as differentiating this second part, notice it will be easiest if we think of it as 9/2 plus 1/2 x squared, because the derivative of 9/2 is 0, and then we can apply the power rule here, 1/2 times 2x to get the derivative of that second term. No need to apply the quotient rule to that one. Now, the good news is the calculus is finished. The most challenging part of some of these derivatives, as you'll see, is simplifying them algebraically. We'll know they're simplified when they have been whittled down to a double-decker fraction. Okay, so I'm going to do some canceling here. Those 2's are going to cancel. Notice on this leftmost term we have 6 times 1/3. 6 times 1/3 is 2. So we could simplify this first term to 2 over 1 plus, let's go ahead and square, x squared over 9 plus 0, which we can leave out, plus x. Now, notice we have 3 levels in that fraction on the left. To cure a complex fraction, we can multiply the top and the bottom by the lowest common denominator of all of the terms in the fraction. So I'm going to multiply the top by 9, and I'm going to multiply both terms in the bottom by 9. This yields 18 over 9 plus, on this term, the 9's cancel, and we get x squared plus x. Now, that's not too bad, but I think we could do a little bit better. Let's go ahead and join these 2 algebraic functions into a single fraction. So dy over dx with a common denominator of 9 plus x squared. Now it's going to look like 18 plus x times 9 plus x squared. Notice we have the original numerator here because that first fraction already had the denominator. On our second fraction, our denominator was 1. We've gained a factor of 9 plus x squared, so we multiply the numerator by that as well. Just algebra stuff. Now, let's distribute our x inside our parenthetical element. And I'm going to rearrange it in descending order in both the top and the bottom, and we'll have a very presentable derivative. So observe on this problem, once again, that the calculus was done after this first step. All of the rest of this stuff was algebra leading us up to the final answer. So this is going to take some practice. hang in there. The more you practice, the easier it gets.